Hey everyone, welcome back. Today we are looking at another key Kubernetes interview question that you are almost certain to run into. This video is regarding a Liveness readiness probe failure. This scenario is a bit long, so I will pin the full text in the comment and drop a link to the GitHub repo in the description. But here's the core of what's going on. We are looking at two Java services running on Kubernetes that both broke under heavy traffic, but for completely opposite reasons. The first service kept running out of memory and getting killed, ending up stuck in a restart loop. What's the problem here? Its readiness probe stayed green right up until the exact moment the pod died. So the load balancer just keeps sending traffic to pods that were literally seconds away from crashing. The second service had the opposite problem. Its liveliness probe was too sensitive. It kept restarting pods during normal Java cleanup pauses, totally mistaking a brief pause for a dead app. At its core, this question is testing something simple. Do you actually understand how Kubernetes health checks, Java memory settings, and load balancers work together in real life? As an interviewer wants to see if you can set up probe logics properly, tweak settings so normal pauses don't trigger bad restarts, and stop memory crashes at the root. On the top of that, they're checking if you can spot these issues in Grafana, and if you know why trying a health check directly on a database is a bad idea. Now let's check the answer. The answer is divided into 5 parts. The first part is the difference between liveliness and readiness. We need to know the real distinction. A liveliness probe should only answer, is this process's own control flow stuck? It should never call out a database or downstream service. A readiness probe answers, can this pod serve a request right now and can legitimately depend on downstream health. To see current probe config on a running probe, we need to run kubectl get pod, then a pod name -o and YAML, and this command will be piped to grep-a8. Then we need to mention liveliness probe, then readiness probe as well. What this command does is pull up a pod's YAML configuration and filter out just the health check settings so you can inspect them quickly. First, kubectl get pods fetches your target pod from the cluster, and then -o YAML flag output its entire configuration in a raw YAML format instead of standard summary view. Next, the pipe symbol takes the entire YAML output and streams it right into grep. From there, grep searches for line containing either liveliness probe or readiness probe using the pattern liveliness readiness probe. The 8 part stands for after 8. It tells grep to print the matching line plus the next 8 lines below it. That's super handy here because probe parameters like the path, port, timeout, and failure thresholds are indented underneath the main probe header in YAML. So running this gives you a net compact snapshot of how both probes are set up on that probe without having to scroll through hundreds of lines of manifest codes. Next, we need to check fixing the gpause flapping. Gpause is garbage collection. GC means garbage collection, so GC is basically automatic memory cleanup for your code. In languages like Java, Go, Python, or JavaScript, you don't have to manually allocate and free up memory every time you create an object. Instead, a background process called the garbage collector keeps track of everything for you. It scans memory for data your app is not using anymore and clears it out so new requests can use this space. Without garbage collection or manual cleanup like you do in C or C++, unused memory just piles up, leading to memory leaks that eventually crash your app. The catch is that garbage collection comes with a trade-off called GC pause, where the collector needs to do a big cleanup. It briefly freezes all application threads, what people often call a stop the world pause. In a Kubernetes environment, if one of those pauses lasts 5 or 10 seconds, the Kubernetes might think your app is hung timeout on a liveliness probe and kill a perfectly healthy container for no good reason. First confirm it's actually liveliness killing the pod and not something else. For that, we run 3 commands: kubectl describe pod, then a pod name, kubectl get pod, then pod name -o JSON path, kubectl log pod, then previous. The flag is previous. These 3 commands make a simple triage workflow for troubleshooting why a container got killed and restarted. First, running kubectl describe pod, then a pod name gives you a detailed overview of pod status. The real gold mine here is the event section at the bottom. If a liveliness probe failed, Kubernetes log it right there with message like liveliness probe failed with status code 500. You can also check a container's last state to see exit codes. You can also check the container's last state to see exit codes, like an exit code 137 for an out of memory killed, like an exit code 137 for an out of memory kill. Second, if you just want to know how many times a pod has restarted without digging through a wall of text, you use kubectl get pod and the pod name -o JSON path. The o JSON path flag filters the raw pod status to pull out just the integer tracking restarts for the main container. Finally, kubectl log pod -previous -previous gets you the log from the container instance that just died. Standard kubectl logs only show output from the newly restarted container, but by adding -previous flag lets you see what the application printed right before it got killed. After all these commands, we need to correlate the timing against real garbage collection pause data. If garbage collection logging is enabled, pull the pause time directly. For that, we run two commands: a kubectl execute pod -jstat and -gcutil, then PID 1000. Then you will run the second command, kubectl logs pod, then grep to pause full pause young. The first command, kubectl execute pod -jstat -gcutil PID -10, runs the jstat utility directly inside your running container. The double dash separate kubectl flags from the command running inside, while PID is your Java process ID, which is almost always one inside a container. The -gcutil flag outputs memory usage percentage across space like Eden and old gen, while 1000 tells it to stream a fresh line every second. The key column to watch here are FGC and FGCT, which tracks full GC count and total full GC time. So don't forget, GC is garbage collection. If old gen fills up and full GC time spikes, your app is hitting stop the world pause that freezes application threads. The second command, kubectl log pod pipe grep pause full -pause young, checks if your Java app is printing garbage collection details directly to standard out. It pipes your pod logs into grep using an OR condition to filter specifically for full or young garbage collection pause lines. If your JVM is configured to log GC details, running this lets you cross-reference exact GC pause timestamp with the liveliness probe timeouts recorded in your pod events, making it easy to confirm if garbage collection is killing your pods. If pause duration line up with probe failure, fix the tolerance math. The third part of the scenario is fixing the out-of-memory case, not a probe tuning problem. Confirm the actual termination reason before assuming anything. We need to run these commands. First is kubectl get pod, then kubectl top pod, then kubectl describe pod. These three commands give you a quick way to check if a pod died from running out of memory and see how much RAM it's using right now. First, kubectl get pod, the pod name and output should be in JSON path. This pulls up the pod status and isolates the exact reason the main container last stop. Instead of dumping a bunch of text, the -o JSON path filter prints just the reason string, so you instantly see if it says OOM killed or error. Next, kubectl top pod name checks live resource usage through the clusters metrics server. It shows you pod's current CPU and memory consumption. Comparing that live memory figure against your configured container limits tells you if the pod is creeping back up towards the danger zone. Finally, kubectl describe pod name -grep A3 last state grabs the full pod details and filters specifically for the container's previous state, plus the 3 lines underneath it. This zeroes in on key postmortem details like exit code 137, which confirms the Linux kernel killed the process with a sick kill because this blew past its memory limit. If it confirms OM killed, this is a resource problem, not a probe problem. Fix the request limit and alert on recurrence. For that, we run kubectl get pod command. This actually breaks down into 2 parts. A quick kubectl command to check a pod's resource settings, followed by a promql query asked for firing alerts in Prometheus. First, kubectl get pod name and -o JSON path checks the resource configuration on your main container. the o-json path filters pulls out just the spec.containers.resource object, letting you instantly verify the CPU and memory request and limits set in the spec without dumping the entire YAML file. Second, promql is an alert rule designed to catch containers dying from memory issues. The first half, increase qpod container status restart total. 1 hour greater than 0 checks if the container's restart count has gone up over the last 1 hour. And the operator links that restart check directly to the second condition. The qpod container status lasted terminated region equal om killed equal to 1. The second metric comes from kubestate metrics and actually like a flag, returning a 1 when the last exit region was specifically an OOM kill. So joining them with and ensures you only trigger an alert when a pod has actually restarted and the root cause was running out of memory. Let's move to the part 4 of the scenario. Here we check probe misconfigured or it's generally unhealthy. For that we use promql queries. These two promql queries let you compare container restart against actual application errors. So you can figure out if a pod is restarting because of a bad health check startup or a genuinely broken app. In the first query, rate qpod container status restart total 5 minutes. This tracks how fast your container are restarting across 5-minute windows using cluster metrics from kubestate metrics. The second query, rate http request total, and the status is 5 minutes, measures the rate of 500 level HTTP errors coming directly out of your application over that same 5-minute period. When you graph both of this together in Grafana, the pattern gives you the answer instantly. If your container restarts suddenly, jump, but your 500 errors rate stays flat. That's a classic problem, meaning the app itself is fine, but an over eager liveliness probe is killing it during something like a brief garbage collection pause. On the flip side, if both restarts and 500 errors spike at the exact same time, the app was actually throwing errors and failing before Kubernetes steps it to restart it. Also, we probe latency creeping up. This promql query calculates the average time your nodes take to run health checks after 5 minutes window. It works by taking the total time spent running probes tracked by a kubectl probe duration seconds sum and dividing it by the total number of probe atoms tracked by kubelet probe duration seconds count. Using the rate function over a 5 minutes window for both parts give you a clean average response time per check. Tracking this is super useful because if your average probe latency creeps up close to your configured timeout seconds, say it's average 1.8 seconds on a 2-second timeout, any minor CPU spike or network hiccups will push this over the edge. That triggers false probe failure and unnecessary starts, even when the application itself is working just fine. This promql query measures how often your containers are getting hit with CPU throttling over a 5 minutes window. Whenever a container burns through its assigned CPU limit, the Linux kernel temporarily freezes its thread until the next scheduling cycle begins. The metrics container CPU CFS throttle period total tracks every single time one of those freezes happen, and wrapping it with the rate 5 minutes calculates how frequently these pauses are occurring per second. Watching this metrics is huge because CPU throttling is one of the biggest hidden causes of fake probe failure. If a container gets frozen right as the kubelet pings its health endpoint, the response thread cannot execute in time. The probe times out and Kubernetes kills a completely healthy container, thinking it's stuck and you would never catch it using standard tools like kubectl top because throttling does not show up as high CPU usage. In the final stage of the scenario, we check if health endpoints calling a DB data. For that, we need to check whether the probe endpoint itself is slow, which is a strong signal it's doing synchronous downstream work. For that, we run kubectl execute pod -f term curl as. This command gives us a quick hands-on way to test a pod's health endpoint from the inside and see exactly how long it takes to respond. The kubectl execute pod command. This part tells Kubernetes to run a command directly inside your target container using the double dash to separate kubectl flags from the actual shell command. Inside the container, it runs time wrapped around curl -s, localhost 8080-health. The time utility measures how long the request takes from start to finish, while curl-s hits your local health endpoint on port 8080 in silent mode so progress bars don't clutter your terminal. Running this directly against localhost is super useful for troubleshooting probe timeouts because this completely bypass external networks, load balancers, and ingress controllers. If a simple HTTP request takes 2 seconds to respond here, you might right away take the slowdown is coming from inside the application itself, like a stuck thread, a slow database query, or a background garbage collection pause rather than a network issue. If probe duration tracks DB latency 1:1, that's the smoking gun. Move readiness to cached async health check instead of synchronous DB call on every hit. And that's pretty much everything for today's video. If you want the full note and the flow diagram, I put all of that in channel's GitHub repo. You will find the link right down in the description box below. If this was helpful, hit that like button, drop a comment, and make sure to subscribe so you don't miss out on any of the daily videos coming up. Thanks for watching, and I will see you in the next one.